Hi, my name is Maya Scarpaci. I'm a molecular biology major senior at Cal U. This experiment was for my microbiology class, and I screened local bacterial isolates and tested them for antibiotic properties. Um, our reasoning for this experiment is that we are really having an issue right now in terms of discovering new novel antibiotics, and that has caused a very high rise in the rate of antibiotic resistance being presented by bacteria. Antibiotics have always been extremely useful and helpful for preventing the spread of very harmful diseases ever since the discovery of penicillin in 1928. And ever since then, we did a good job at busting out a bunch of new antibiotics and discovering them. Until about 50 years ago, when we really kind of hit a wall and we entered what's known as the discovery void. There's just a big gap in discovery of new antibiotics for a long time. And because of this, the rates of antibiotic resistance really rised. And bacteria that were once very easy for us to manage, very common, are now posing way larger threats because they have much higher rates of antibiotic resistance, and the antibiotics that we have are not working for them. So there's definitely a need for discovery and research into new antibiotics. And with the knowledge that antibiotics come from bacteria, there's no better place to try to find bacteria than in the soil around you. So I took soil from the nearest park. I followed the tiny earth methodology for this experiment. I went to SAI Park, which is a park near my house, and collected some soil. When I tried to pay close attention to the possible biodiversity of the area that I was sampling from, I really wanted to make sure that I took soil from an area that I believed can bear multiple different kinds of bacteria, so I can get much better results. I took my soil back, and once I plated it, I chose 12 isolates that I wanted to continue on with experimentation, and I screened them for antibiotic properties that they could be producing by covering 3 plates with 3 different pathogens and plating my 12 isolates over top in the hopes that I would see a halo or clearing of growth surrounding the isolate, indicating that it inhibited the growth of the pathogen around it. After that, I took some of the isolates and performed some biochemical tests on them, like a nutrient gelatin test, an oxidase test, and a catalase test, to try to get a better idea of what kind of enzymes these bacteria are capable of producing. So for my results, you can see in figures A and B, I actually did come back with 2 of my isolates had antibiotic properties that they were releasing. Isolates MJS4 and MJS6 produced an antibiotic that inhibited the growth of P. aeruginosa. You can see the halo, the clearing of growth around the isolate, indicating that it definitely inhibited the growth of the pathogen. These 2 bacterial isolates did not inhibit any other pathogens that we tested. So it just, and P. aeruginosa is gram-negative, and so is E. coli, so I can't conclude with confidence that isolates MJS4 and MJS6 can definitely release antibiotic properties towards all gram-negative bacteria, so there's definitely a lot more research that needs to be done with those 2 isolates. My isolate 8, I had to plate separately from my other isolates just because I needed a couple more days to get some more isolated colonies to grow so I could use them for experimentation. So I plated those separately, and for the E. coli plate, the P. aeruginosa plate, and the S. epidermidis plate, I got negative results for all 3 of them, which was surprising to me because initially when I created the master plate of all my 12 isolates, one of my isolates had overgrowth and contaminated other boxes on the master plate, and isolate 8 actually showed a clearing of growth, inhibiting the growth of isolate 9. So isolate MJS8 was the first isolate to show any antibiotic properties before I was even necessarily performing a test for antibiotic properties. So I had a lot of high hopes for MJS8. Didn't show any results for these 3 specific pathogens, but that just means that it may need to be tested against some other ones. The nutrient gelatin test, no pictures available due to a technical issue, but all for MGS4, MGS6, and E. coli and B. subtilis were used as controls. All 4 results were negative. It was indicated by solid gelatin after 1 week. That tells us that my isolates are not capable of producing, or did not at that moment have, the enzyme gelatinase. The oxidase test is the same thing, got 4 negative results, showing that at this specific point in time, at least, my isolates MGS4 and MGS6 were not capable of producing the enzyme cytochrome C oxidase. For my catalase test, however, I got positive results for my isolates MGS4 and MGS6, which was indicated by the presence of bubbles. So I was able to conclude that these 2 isolates were able to produce the catalase enzyme. Knowing what kind of enzymes that your bacteria can produce can really give you some clues as to what type of antibiotic that it may be producing. So my initial hypothesis that the soil that I sample will most likely contain a bacterial isolate that is capable of producing an antibiotic, that hypothesis was definitely supported by my results. I would like to move forward with experimentation in isolates MGS4, MGS6, and MGS8, because those were the only 3 that showed antibiotic properties at some point in the experiment. Since we only experimented with these 3 different kinds of pathogens, there's much more that can be done to definitively conclude what kind of antibiotic these bacteria are producing. In the future, I definitely would like to test these isolates against pathogens with different characteristics, modal versus non-modal, gram-negative versus gram-positive, capsulated versus non-encapsulated. All these characteristics can definitely make a big difference on whether or not the bacteria can produce an antibiotic that is effective against it. So testing them against as many different kinds as possible can give you the most accurate understanding of what this bacteria can actually produce. Same with doing the biochemical test to understand the enzymes. That can help you understand the mechanism of the antibiotic and how it actually works. Also, I would like to do some genomic annotation to try to see if my isolates that I have are novel isolates or if it's something that's already known in science. Ultimately, the goal throughout all of this is to be able to find a new antibiotic that I can add to the Tiny Earth database. That would be extremely helpful for continuing on the search for novel antibiotics and trying to contribute to the fight against antibacterial resistance is definitely extremely important research that we need to continue to go on with. So I'm definitely would have a lot more ideas and further experimentation that I can do with my isolates. Thank you.